Good evening, everyone. Welcome to York's Observatory TeleTube, the online astronomy and astrophysics program ran and presented by the students, faculty, alumni, and friends of York University. We are broadcasting live from the Alani Carswell Observatory, located at York University in Toronto, Ontario, Canada. TeleTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. Any questions or comments you have about our past shows, or if you have any suggestions for future topics, please send us an email at observe@yorku.ca. You can also connect with us on Twitter or Instagram with the handle @York Observatory and Facebook at Alan I. Carswell Obs. I'm Obada, and I'll be one of your hosts this evening, along with Arfa, Matt, Maheen, and Sergiy. Tonight we have an awesome presentation about the Alpha Centauri system. But before we get started with our main show, we want to give you a little update on what you can see this coming week. In Toronto, right after sunset at around 8:40 p.m., you can just catch the evening star, also known as Venus, setting with the sun in the west-northwest part of the sky. At the very early morning of today, parts of Earth were able to see a lunar eclipse, but unfortunately it was not visible from Toronto. However, you can still see the regular full moon rising tonight from the southeast part of the sky at around 10 p.m. and set around 5 a.m. Just an FYI, eclipses usually come in pairs, and there is usually an annual solar eclipse due just visible from the Toronto area on June 10th. Keep this page bookmarked, as we will do a special event for the eclipse on June 9th and the 16th. While you are looking at the moon tonight, you can also catch some interesting constellations, such as the Cygnus constellation, the star Vega, and the Andromeda constellation, much later on in the night. You can also catch Jupiter and Saturn next to each other at around 3 a.m. They'll appear as two bright stars, where the dimmer one is Saturn. Try and spot these constellations and objects if you have clear skies. A pair of binoculars or small telescopes are excellent options to see some deeper space objects, just such as clusters or nebulae. Let us know what you can see in the chat below. Now, without further ado, let's get started. Arfa will start us off tonight with an introduction to the Alpha Centauri star system.
So today we will be talking about the Alpha Centauri system, but before we go into details, let's discuss what star systems are. A star system, or also known as stellar system, is basically a small number of stars that orbit around each other. If there is a large group of stars bound together by gravitational forces, it is known as star cluster or a galaxy. However, they should not be confused with the planetary system, which includes planets and other celestial objects like comets. If a star system consists of two stars, it is known as a binary star system. Examples of binary systems are Sirius and Cygnus X1. Introduction to the Alpha Centauri. About 10% of the star systems are triple star systems. They are thought to form when three stars are bound together out of the same disk of gas and dust. An example of a triple star system is Alpha Centauri, which is located just over 4 light years, or about 25 trillion miles from Earth. While this is a large distance, this is a large system in distance in terrestrial terms, it is 3 times closer than the next nearest sun-like star. The two stars in Alpha Centauri systems are a pair called A and B, or AB for short. They orbit relatively close to each other. Alpha Centauri system also consists of a third member, Alpha Centauri, also known as Proxima, which is a much smaller red dwarf star. My colleague Sergiy will discuss more about its fascinating details ahead. Proxima currently holds the title of the nearest star to Earth, although AB is very close second. Alpha Centauri A and B are sun-like stars classified as class G and K, and together they form the binary star Alpha Centauri AB. To the naked eye, the two main components appear to be a single star with an apparent magnitude of 0.27. Alpha Centauri B. Alpha Centauri B is also known as Toyman. It is the secondary star of the binary system. It is the main sequence star by spectral K1V, making it more an orange color than Alpha Centauri A. This star is smaller than our star's sun, having a mass of about 90% of that of Sun and about 14% smaller in diameter. In comparison to Alpha Centauri A, Alpha Centauri B emits more energy in the X-ray band. Not only it emits more energy than Alpha Centauri A, it is more magnetically active than Alpha Centauri A, showing a cycle of 8.2 years compared to 11 years for the Sun. and about half the minimum to peak variation in coronal luminosity of the sun. Its light curve varies on a short time scale, and there has been at least one observed flare. Alpha Centauri b has an apparent magnitude of plus 1.35. The orbital speed of Alpha Centauri A and B stars are 79.91 years. The orbit of these two star systems is moderately eccentric, which is 0.5179 approximately. The two main points in the orbit are called perihelion, which is the closest point to the star, and apastron, the furthest point. These stars have a perihelion of 11.2 AU, or let's say in other units, 1.68 billion kilometers. That's roughly the distance between the Sun and Saturn. Apastron of 35.6 AU, which is 5.33 billion kilometers, and that would be around the distance between our Pluto and Sun. August of 1955 was the most recent peristron that occurred and next will be occurring in 2035. Talking about the apastron, which occurred May 1995, not that long ago, but the next one will happen in 2075. If observed from Earth, it seems as if the orbit of these two stars are continuously changing their separation and position angle as they move around their orbit. For example, as per the data collected in 2018, these stars were separated by 4.92 arc seconds at a position angle of 337.1 degrees. When observed in 2020, the separation had increased to 5.49 arc seconds through 345.3 degrees. The closest these stars have been observed was at 4.0 arc seconds through the position angle of 300 degrees in February 2016, and maximum is about 22 arc seconds. Now, Maheen will tell us more about Alpha Centauri A.
Thank you, Arfa. As Arfa introduced the Alpha Centauri star system, one of the stars in this system is Alpha Centauri A, also known as Rigil Kentaurus, which comes from Rigil al-Kentaurus, which is the Arabic for foot of Centaur. It forms a pair with Alpha Centauri b, which orbit close to each other. For this section, we will mostly focus on Alpha Centauri A, which is the brightest star of the Alpha Centauri star system. This star is very similar to the Sun in spectral type, absolute magnitude, and diameter, so much that it can be called a Sun's twin, even in terms of its age. Alpha Centauri A is the third closest star to the Earth at a distance of 4.364 light-years. For reference, 1 light-year is equivalent to 63,241.1 AU. Alpha Centauri A is yellowish in color. It is a bit more massive than Sun and also 1.5 times brighter. It is about 5 to 6 billion years old. Since Alpha Centauri A and B are a pair, they're gravitationally bound together and orbit about a common center of mass every 79.9 years at a relatively close proximity, that is ranging from 40 and 47 astronomical units. For reference, the distance between Earth and Sun is 1 astronomical unit. The star has a surface temperature of 5,790 Kelvin. It can sometimes be complicated to view the star, especially the northern hemisphere is unlucky in that respect, since it is more on the southern side of the sky, that is, it is in the southern constellation Centaurus. It can only be seen from the south of 40° north latitude. As we discussed, the star is very similar to the Sun. It shows coronal variability due to star spots, which are dark blotches on the star's surface due to a cooler temperature than the surrounding areas, as modulated by the star's rotation. The activity level of the corona for the star has fallen into a deep minimum since 2005, which has been suggested as being similar to Sun's modern minimum, or it may just have a very long stellar activity cycle causing it to slowly recover from a minimum phase. Bringing in the topic of exoplanets for the star, a lot of work is being done to find any potentially habitable worlds hiding around the star. This work includes the use of giant telescopes in Chile, use of new high-precision starlight sifting instruments, development of low-cost satellites for planet hunting in space, etc. Just as suggested by the astrophysicist Ruslan Belikov of NASA's Ames Research Center, quote, "The level of interest in finding them is definitely increasing." Unquote. From the input of all the work, a potential habitable zone planet around Alpha Centauri has been found. The initial observations were made by the European Southern Observatory (ESO for short) Very Large Telescope at the Paranal Observatory in Chile as a part of NEAR, New Earth in the Alpha Centauri region program. A bright thermal imaging signal was detected coming from the habitable zone of Alpha Centauri A. This detection was possible due to the upgrades on the VLT, which is ESO's Very Large Telescope. These upgrades included a thermal chronograph which blocks stellar light and looks for heat signatures coming from planetary objects as they reflect light from their star. The signal was found after the analysis of 100 hours of data in May and June of 2019. That is, we can say exactly 2 years prior to today. Yes, it is still a question. It has not yet been verified that the planet exists, and so it does not have a name, although the signal does suggest that it is the size of Neptune. The size of the planet suggests that the mystery planet isn't Earth-like, rather a warm gas planet 5 to 7 times larger than Earth. Considering how habitable it is, it's most probably only suitable for microbial life in the clouds. The reason for still questioning the existence of the planet is because the signal received can be reasoned using other theories as well. It could just be caused due to hot cosmic dust, stray photons, or a more distant object in the background. In order for the confirmation of the planet's existence, another observation of the object will have to take place to determine its position, and whether its new position corresponds with an orbit. It was found that the planet is potentially orbiting at a distance of 1 to 2 astronomical units from the star. I will now pass it over to Sergiy to tell you more about Proxima Centauri.
Thank you, Maheen. Out of the 3 Alpha Centauri stars, the last one is Alpha Centauri C. A more common and famous name for this star is Proxima Centauri, which is Latin for the nearest of Centauri, as it is the closest star to Earth, not including the Sun, at 4.2 light years distance away, and is located in the constellation Centaurus, although it cannot be seen with the naked eye. Proxima Centauri has been the Sun's closest neighbor for around 32,000 years, and will stay like that for another 25,000 years. Due to the progression of the stars in their solar orbits, the tidal of the closest star to the Sun will alternate approximately every 80 years between Alpha Centauri A and Alpha Centauri B. You can see Proxima Centauri C on your screen right now within the red circle. Proxima Centauri is an M5.5 red dwarf, meaning that it has less mass than other M-type dwarf stars, which are the most common star type in the Milky Way. Namely, it has only 12% of the Sun's mass, but it is 33 times as dense as our Sun. The low mass of Proxima Centauri causes it to have most of its energy transferred within the interior of the star through convection, as can be seen from the image on the right. This is unlike larger stars, which transfer energy outside the core through radiation, or use radiation in the core and convection outside of it, as can be seen on the image to the left and in the middle, respectively. Through convection, helium ash, which is what energetic helium-4 nuclei or alpha particles are called, left over from the fusion of hydrogen, is circulated throughout the star instead of being concentrated at the core. If we compare Alpha Centauri C with the Sun, we can see a difference in the amount of hydrogen supply that is consumed in the star by fusion. The Sun uses around 10% of all its hydrogen, whereas Proxima Centauri will use nearly all of it until it runs out of hydrogen in around 4 trillion years. Additional characteristics of Proxima Centauri include the fact that it is only 0.15% as luminous as the Sun, and has a radius that is 14% of the radius of the Sun. No wonder it is difficult to see. Convection in the core of Alpha Centauri C causes a magnetic field whose magnetic energy is released at the surface of the star as short stellar flares. Some of these stellar flares are so short that they only last 10 seconds. Due to it being smaller than the Sun, it loses 8 times more mass per unit surface area as compared to the Sun from its relatively weak solar winds. Recently in 2016, Proxima Centauri B was confirmed. It was first spotted in 2013 at a distance of 0.05 astronomical units or 7.5 million kilometers away from its host star, with an orbital period of around 11.2 days with a mass of at least 1.17 times that of Earth. Like Earth, it is a planet that orbits the sun, the star within its habitable zone, allowing for the possibility of liquid water to exist on its surface. The great scientific progress to find a planet of a very dim star took considerable effort and multiple years of high-precision radial velocity monitoring. This shows that it is possible for planets to form around low-mass stars. Proxima Centauri b will further be used to advance the knowledge of the evolution of the magnetic dynamo and how stellar activity affects planetary atmospheres, as red dwarfs like Alpha Centauri c are, relative to other stars, small, cool, and have a low luminosity. First postulated in 2019 and confirmed in 2020, Proxima Centauri c orbits Proxima Centauri in a 1.5 AU or 220 million kilometer orbit that takes around 1900 days or 5.2 years to complete. The second planet is known as a super Earth and a mini Neptune, as it resembles the gas giants in that this frozen planet is covered in a gas 6 to 8 times as heavy as the Earth. Not much is known about this planet, but some of the data suggests that it might have a ring system and that its skies may be colored by auroras due to its magnetic field interacting with intense flares from Alpha Centauri c. Both planets were found from the same multi-year dataset from the European Southern Observatory's ESO HARPS instrument. The paper you see on the screen right now, a terrestrial planet candidate in a temperate orbit around Proxima Centauri, is the one that confirmed the existence of Proxima Centauri b, saying, and I quote, "Since the analysis of the activity data failed to identify any stellar activity feature likely to generate a spurious Doppler signal at 11.2 days, we conclude that the variability in the data is best explained by the presence of a planet, Proxima b hereafter, orbiting the star." In later publications, Proxima Centauri c was analyzed to measure its wobble that is caused by possible planets. The mass of the planet could be estimated from the strength of the wobble, whereas the planet's orbit could be estimated from the period of the wobble, or in other words, how long it takes to complete one cycle of the wobble. In the case of Proxima Centauri c, it causes the host star to wobble 1 meter per second. There may be another exoplanet orbiting Alpha Centauri c, which, if true, will be given the name Proxima Centauri d, though it is still unconfirmed. Next up, we'll have Matt explain future missions to the Alpha Centauri system.
Thank you, Sergiy, for those amazing details about the exoplanets and stars found in the system. Now that we know what makes the Alpha Centauri system so interesting and appealing to investigation and future research in order to find habitable or Earth-like planets, we as humans always have the desire to aim for the stars and to try to reach them. And the Alpha Centauri system is not the exception. Since we have mentioned on this presentation the several potentially habitable planets that could even harbor some type of extraterrestrial life, scientists have been trying to figure out a way to reach this system. That even though it is the closest one, the closest system to ours, it is extremely far away from us with the technology we can have right now. As a matter of fact, if you may have seen our other teletubes mentioning the Voyager probes and their current final destination per se, it has been almost 50 years since they were launched, and they have just reached the limit of the heliosphere and have entered the so-called interstellar space. But to make this distance clear, at more than 56,000 kilometers per hour, it would take the Voyagers at least 40,000 years to reach the Alpha Centauri system. This is like saying we have achieved a 4-minute walk from the Allen I. Carswell Observatory to York University Station in 44 years while trying to get to Argentina. So again, they are traveling at thousands of kilometers per hour, and still we haven't even done a mere 5% of the trip. So how can we travel or send the probe light years away from Earth? Well, that's exactly what the Breakthrough Starshot, Starlight, and Project Longshot are trying to achieve. The first and most famous project related to the Alpha Centauri system is the Breakthrough Starshot project, financed by several renowned billionaires, scientists, physicists, and astronomers. such as Mark Zuckerberg himself, Neil deGrasse Tyson, and Andrew Pete Warden, and even the late scientist Stephen Hawking. The Breakthrough Starshot project plans to launch thousands of probes heading to the Earth-like exoplanet Proxima Centauri b, orbiting Proxima Centauri in 2069. Yes, you heard it right, 2069. So what is the plan for the mission? What are we supposed to do in order to travel 4.3 light years in less than 30 years? Well, the answer is light. We know that we cannot achieve the speed of light as it was theorized by Albert Einstein himself, but what if we manage to get a velocity of 15 or 20% the speed of light? Is it possible? Well, the theoretical answer is yes. All we need is a light beam and thousands of nanocrafts or extremely small probes that will sail like light, just like a boat. And instead of wind, we'll use the power of a light beam or at a gigawatt potential. And no, it's not going to be the 22 gigawatts required for Marty McFly to travel back to the future, but a whopping 100 gigawatt level light beam powering the photon thrusters and the light sails added in the nanocrafts. It is a pretty exciting project, and we know that most of it sounds like science fiction right now, just like Back to the Future. But in reality, the concept is plausible and has been studied and proposed by since 2016 by several professors, scientists, and physicists from Harvard all the way to the European Space Agency, NASA, and other space organizations with the sole purpose of achieving this new big step for humanity. And this is not the only project trying to get to the closest system we have. We also have the Starlight Interstellar Probe, which is similar to the Breakthrough Starshot project, because the Starlight Interstellar Probe, also known as the Deep-In project, as in directed energy propulsion for interstellar exploration, is a mission performed by the UCSB Experimental Cosmology Group and directed by NASA's Division for Innovative Advanced Concepts, aiming to use the same concept as a Starshot and use a large-scale directed energy to propel a small spacecraft to relativistic speeds. In other words, photon propulsion that would help the minuscule probes achieve the speeds of even 0.25 the speed of light. It is a project currently managed by Dr. Phil Luban and designed by Robert Salazar, who is specifically in charge of designing the laser beam that will provide the power to send the nanocrafts and propel them to where no human-made object has ever been. As a matter of fact, it is already a prototype built in a smaller scale of this laser beam, composed of an hexagonal array with less power than what they are trying to do or they're trying to achieve, of course, but with the same concept that with the right tools, time, and resources, it will turn out into one of the biggest projects that JPL and NASA has directed. Unlike the other two missions, the Project Longshot mission wasn't a light propulsion probe headed to the Alpha Centauri system, but actually a nuclear one, specifically nuclear pulse propulsion, which consists of creating thrust thanks to the several explosions created by a nuclear reactor inside a probe. This was first tested back in 1947 and the late 60s in several military projects such as the Project Orion, Project Daedalus, but it wasn't until the late 1980s when NASA decided to repurpose this idea and sponsor it with the objective of reaching Alpha Centauri in record time. Now, even with this vanguardist technology for the century, scientists have calculated that it would take at least 100 years to reach the neighbor system. And it's actually not that bad if you take into account that it would mean that its speed would be at least 5% the speed of light. Not as fast as our light probes, yes, of course, but fast enough to get to its target. And well, now there are many other ideas to reach our closest stars, such as more of theoretical types of propulsion, um, such as the antimatter catalyzed nuclear pulse propulsion. But that honestly sounds like it deserves a TeleTube of its own, right? And well, everyone, you have been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the astronomy and astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Obada, Maheen, Sergiy, Arfa, and myself, Matt. Make sure to leave any comments or questions in the comment section of the video and talk to us right now in the chat. We will be around for the next 20 minutes to answer all of your questions. And all of our programs are free, by the way. But if you would like to make a donation, you can see our website at observatory.info.yorku.ca, where you'll also find an incredible opportunity for sure you wouldn't want to miss. As a matter of fact, our astronomical calendars are 50% off. Yes, you heard me right, 50% off. So make sure you check that out if you're interested in having a piece of astronomical memorabilia at home. You can also connect with us always on Twitter with the handle @York Observatory, and check out our website for show notes, content, updates, and contact info. As I mentioned before, at observatory.info.yorku.ca. And this has been the end of it. Thanks for tuning in. Clear skies and have a great night.